In Chapter 1 on functions and graph, we will continue with our discussion of functions and their graphs. In the first example, we want to determine whether or not the relation is a function. You recall the definition of a relation. A relation is any set of ordered pairs. So we have the given set of ordered pairs, and we want to, well, it is a relation. Now we want to determine if this relation is a function. You also remember or recall the definition of a function. In a function, we said that for each x element, there is assigned exactly one element in the range of the function. So let's see what happens. 1, 2, 3, 4, 5, 6. 5 is mapped to 6. 5 is also mapped to 8. So what's happening here is that we have two elements in the range for y. This violates the definition of a function. For each x, there's only one y, but for 5, we have two different y values. So therefore, this is not a function. Is this a function? No, not a function. In the next example, you have a set of ordered pairs. And again, we want to decide or determine if this set of ordered pairs represents a function. For each x, 1, 2, 3, 4, 6, 5. Indeed, for each x, there is only one y. So therefore, this set of ordered pairs represents a function. So yes, it is a function. Given a function, the definition of a function, f of x, in this case, if f of x is equal to x squared minus 2x plus 7, we want to now evaluate the function at a negative 5. Negative 5 is, of course, in the domain of that function. So to find f of a negative 5, we want to substitute a negative 5 for x in the definition of the function. In the definition of the function, we have x squared, so that's going to be a negative 5 squared minus 2 times the negative 5 plus 7. A negative 5 squared is 25. A negative 2 times a negative 5 is a positive 10 plus 7. So we have 35, 25 plus 10 is 35, plus 7 is 42. So therefore, f of a negative 5 is 42. Now, let's evaluate the function f at x plus 4. So what do we have? We have x squared, so that's going to be x plus 4 squared minus 2 times x plus 4 plus 7. X plus 4 squared is going to be, you can either use the FOIL method and write this as x plus 4 times x plus 4 minus 2 times x plus 4 plus 7. All right, so let's simplify. Let's do this multiplication first. So that's x squared plus 4x plus 4x plus 4 times 4, 16. Minus 2 times x is a minus 2x. Minus 2 times a positive 4 is a negative 8 plus 7. So we have x squared. Let's combine like terms. Combining like terms, we have 4x plus 4x is 8x plus 16 minus 2x minus 8 plus 7. X squared plus 8x minus 2x is a positive 6x, and a negative 8 plus 7 is a negative 1. A negative 1 plus a positive 16 is a positive 15. So therefore, f of x plus 4 is x squared plus 6x plus 15. In the last example, f of minus x. In this example, we're replacing a negative x for x. So this is going to be a negative x squared minus 2 times the negative x plus 7. A negative x squared is x squared. A minus 2 times a negative x minus times a minus, a positive 2x plus 7. So therefore, f of minus x is x squared plus 2x plus 7. The next example involves graphing two functions in the same rectangular coordinate system. So we're going to graph the function f of x is equal to 2x, and the function g of x is equal to 2x minus 3 in the same rectangular coordinates. In the next example, we are asked to graph two functions in the same rectangular coordinate system. All right, in order to do that, let's create a table of values for the first function. F of x is equal to 2x, and we're to use values of x between a negative 2 and 2. X is a negative 2, so 2x is going to be 2 times a negative 2, and the corresponding ordered pair is 2 times a negative 2 is a negative 4, so the ordered pair is going to be a negative 2, negative 4. The next x value is a negative 1. So 2x is going to be 2 times a negative 1, which is a negative 2. The corresponding ordered pair is a negative 1, negative 2. When x is 0, 2 times 0 is 0. The ordered pair then becomes 0, 0. When x is 1, 2 times 1, which is 2. So the corresponding ordered pair, the x coordinate is 1, and the y coordinate is 2. When x is 2, the y coordinate is 2 times 2, which is 4. The corresponding ordered pair is 2, 4. So we have the coordinates of the first function. F of x is equal to 2x. In a minute, we will plot these in the rectangular coordinate system. Let's get the coordinates of gx is equal to 2x minus 3. Using the same x values here, minus 2, minus 1, 0, 1, 2. So when x is a negative 2, to compute the corresponding y coordinate, the definition of g says that we should multiply the x coordinate by 2. So that's 2 times a negative 2 and subtract 3. When we do that, 2 times a negative 2 is a negative 4. A negative 3 plus a negative 3 is a negative 7. So the corresponding ordered pair is a negative 2, negative 7. When x is a negative 1, we have 2 times a negative 1 minus 3. 2 times a negative 1 is a negative 2. A negative 2 plus a negative 3 is a negative 5. The corresponding ordered pair is a negative 1, negative 5. When x is 0, we have 2 times 0 minus 3. 2 times 0 is 0, minus 3 is a negative 3. The corresponding ordered pair is 0, -3. When x is 1, we have 2 times 1 minus 3. 2 times 1 is 2, minus 3 is a -1. The corresponding ordered pair is 1, -1. When x is 2, we have 2 times 2 minus 3. 2 times 2 is 4. 4 minus 3 is 1. So the corresponding ordered pair is 2, 1. Now that we have these ordered pairs, we need to plot each point in the the same rectangular coordinate system. In the next example, well, we want to continue here. We want to now graph the two functions in the same coordinate plane. We have the ordered pairs, so let's graph. For the first function, f of x is equal to 2x. The ordered pairs that we generated are listed. So let's graph the first point, a -2, -4. So these are -2, -4, 0, -1, -2, -3, -4, -5, -6, -7. The next point is a -1, -2. A -1, -2 is here. 0, 0 is here. 1, 2. The x coordinate is 1, the y coordinate is 2. 2, 4. The x coordinate is 2 and the y coordinate is 4. And now to obtain the graph, we connect the points. To graph the next function, g of x is equal to 2x minus 3. We don't want to just plot these points, these ordered pairs that we generated previously. The first ordered pair is a -2, -7, -2, -7 is here. -1, -5, -1, -5 is here. 0, -3 is here. 1, -1 is here. And the last ordered pair, 2, 1. And now to obtain the graph, we need to connect the points. All right, as we connect the points, all right, I'm a little off, but there you are. So we have the two graphs in the same, we've graphed them both in the same rectangular coordinate system. In this example, we will use the vertical line test to identify which graph actually represents the graph of a function. And in the vertical line test, we recall that if we draw a vertical line and the line touches the graph at one point, then we know it represents the graph of a function. So for each vertical line, that line intersects the graph at one point. So we know that the first graph represents the graph of a function. So is this a function? Yes. In the next example, the next graph, if I draw my vertical line, I see that the line intersects the graph in 3 points. So therefore, this graph violates the vertical line test. As a result, we conclude that the graph does not represent the graph of a function. Is this a function? No. In the next example, so let's draw a vertical line. It's good. The line touches the graph at one point. So therefore, this graph represents the graph of a function. Is this a function? Is it a function? Yes. In the next example, vertical line, we see that it violates the vertical line test. So this graph does not represent the graph of a function. Is this a function? No. In this example, given the graph of a function, we can determine the domain and the range of the function just by looking at the graph. So we're going to use each graph here to identify the function's domain and its range. All right, the domain, of course, you're going to look along your inputs, the x. So we look along the x-axis, and we see that a -2 is part of the domain. So we have the domain, a -2, and it's shaded, so the -2 is included. And we go all the way to 2. So the x values of this function are from a -2 to 1. A -2 to 1. All right? So a -2 to 1. Now this is an interval notation. If you like, you could have also represented the domain in set builder notation. The set of all x such that x is greater than or equal to -2 and less than or equal to 1. Now the range, for the range of the function, we want to look along the y-axis. We see that the smallest value of y is going to be 0. All right, so it's 0. And the largest value is 3. So the range, we can see that the values of this function range from 0 to 3. So it's from 0 to 3. Again, in set builder notation, we say that the range is the set of all y values such that y is greater than or equal to 0, less than or equal to 3. In the next example, we want to find the domain. So we're going to look along the x-axis. So along the x-axis, starts at a -2. X is a -2. And notice it's unshaded, so the -2 is not included. So this is going to be a -2 and over to 1. 1 is included, it's shaded. So the domain covers the set of all x values between a -2 and 1. But notice that the circle is shaded, so the 1 is included. So we have open -2, the 1 is included, so we want to use a bracket. So the domain would be the set of all numbers between a -2 and 1. In set builder notation, we would represent this as the set of all x such that x is greater than or -2, but less than or equal to 7. For the range of this function, we're going to look along the y-axis. All right, so we see that the first value of the range, all right, up to 2 and 1, looking along the y-axis. So let's determine the range of this function. So we're going to look along the y-axis. So we see that -1, all right, is the smallest value, and the largest value is 2. All right, so we go, the range using interval notation is going to be from a -1 to 2. And because at 2 the circle is not shaded, the 2 is not included, so we're going to use an open parentheses. So the interval, the range, is the set of all values between a -1 and 2, -1 included. In set builder notation, the range would be the set of all y such that y is greater than or equal to a -1 and less than 2. In the next graph, so let's determine the domain. The domain, the x value, so is a value for a -3. So from a -3, the domain, a -3 over to 0. So it's included, so this is the domain is from a -3 to 0. And the 0, it's an open, so we're going to put parentheses. In set builder notation, the domain would be the set of all x such that x is greater than or equal to -3 and less than 0. The range, so we're going to look along the y-axis. And as we can see here, we have horizontal lines. We have a -3, a -2, a -1. So in the range, we only have integers. So the range would be the set containing the numbers a -3, -2, and -1. So the set of all y such that y is equal to, if you wanted to use set builder notation, such that y is equal to a -3, a -2, a -1. Let's look at one of the homework problems for this section. So we want to use the graph, the given graph, to determine the function's domain, the range of the function, the x and the y intercepts, and then from the graph determine the values of f of -2 and f of 2. So in the first part, the domain. We see that the domain is going to be the set of all real numbers. This is continuous there, so the domain is going to be the set of all real numbers. You can use interval notation, or you could actually just write it out. The set of all real numbers. You can give me a verbal description, or in set builder, the set of all x such that x is a real number. Part B, the function's range. So we're going to look at the graph and determine the values that are represented here. So we see that the highest value of y is going to be 4. All right, and then the values are decreasing here. So the range is going to be, and let's use interval notation here. So it starts at 4. So the set of all y such that the values are less than or equal to 4. So the range then would be the set of all y values such that y is less than or equal to 4. Part C, the x-intercepts, if any. Let's see. Well, there are x-intercepts. As you may recall, the x-intercepts correspond to where the graph crosses the x-axis. So the x-intercepts are a negative 3, 0, and the point 1, 0. Part D, the y-intercept. The y-intercept is where the graph crosses the y-axis. The graph crosses the y-axis at the point 0, 3. 0, 3. So the y-intercept is 0, 3. Part E, looking at your graph, you want to determine f of minus 2. The minus 2 is the x, the input value from your domain. So you go to the graph, negative 2, and you see where. So on the graph, negative 2 corresponds to 3. So f of minus 2 is 3, and f of 2. So on the graph, we go to 2. The x input is 2, and we see where the graph for 2, it's here. So f of 2 is going to be a negative 5.